Do you know that the complex number arises out of a quadratic equation? Do you know that how complex numbers are used in electronics? Do you know what is the difference between complex number and imaginary number? Do you know? Well, the list is quite long. Well, there are many such amazing facts and histories that makes complex numbers an interesting subject to study. In this video, I would be illustrating some amazing facts of complex and imaginary numbers, and you are going to enjoy your future study in mathematics with complex numbers. My name is Shaunak and you're watching this video on my channel Physics for Students. So in this video we won't have any topics, but we will come up with some amazing facts. The first amazing is fact number 1. Well, here I would like to tell is that complex number has relation with quadratic equations, and let me show you how. Now, if the solution to any quadratic equation of the form ax squared plus bx plus c equals to 0 has something like this. This is something very elementary which we have learned in school days. Now, if we try to solve this equation x squared plus 5x plus 10 equals to 0, then we substitute the values, we get this and this. So what happens is that we find out a point in our equation where the square root of minus 5 is something we really don't know. So is there a real number whose square leads to this number? And this is where the complex numbers come in. So you see, the first amazing fact about this study is that complex number arises out of quadratic equations. Now, if you take further things, what we would see is that this part is not real and x is also not real. So what is the definition of imaginary unit number? We define the imaginary unit number I as the square root of minus 1. That is, I equals to square root of minus 1. Substituting the values, we somehow get an approximate value of 3.87i. So you see that what I've tried to demonstrate, that the first amazing fact that it is a simple quadratic equation, but we substitute certain values which results into square root of minus 15, which is actually an imaginary number. So imaginary number is said to be imaginary, a number said to be imaginary if its square is negative. So minus 15 square would be leading to minus 15. So I minus I square root of 15 is an imaginary number, because as you see in this equation I have plotted, and we get the value as minus 15. So isn't it very amazing that out of the simple quadratic equations that we have learned in our school days, we come to something which is an imaginary number. Okay, so we come to the next amazing fact 2. And what is this fact? This fact tells that complex number are used in electronics, and I'm going to show you with a very simple demonstration how it is so. So you see that the I that you use to denote in general mathematics as imaginary number is used as J, since I is a variable denoting the electric current. So a complex number that is represented a kind of a sinusoidal voltage is called a phasor. Well, I'm not going much into phasor, that is a different subject of electronics, but here you can see a demonstration of what is called a direct current and an alternating current. Now when we are dealing with direct current, what happens is that we deal with certain things directly in one dimension, but when we are dealing with alternating current, which is the brainchild of Nikola Tesla, we find that the current, even resistance, are not familiar with one-dimensional quantities. That means that we are used to measuring one-dimensional quantities in direct or DC circuits, which are not found in alternating circuit. So the first thing which comes up, that the voltage produced by a battery, for example, is a scalar quantity. So the resistance of a piece of wire which is in ohms, or the current in amperes. So whenever we analyze AC circuits, we find that the quantity of voltage, current, and even resistance, which we called impedance in AC, are not familiar in one-dimensional quantities. So rather these quantities, because they are dynamic, that means alternating in nature, like the amplitude, possesses other dimension that must be taken into account. Frequency and phase shift, or two of these dimensions that comes into play. Even if we take the simple AC circuits, right, when we are dealing with single frequency, we still have the dimension of phase shift to contend with addition to amplitude. So what we need in order to successfully analyze AC circuits, we need to work with mathematical objects and techniques of which are capable of representing these multi-dimensional quantities, and that is why we need complex number. So what happens is that in order to analyze the AC circuits, we need something which would deal with multi-dimensional quantities which are amplitude and other things, and here we need some mathematical entity which is the complex number. So you see in direct circuit, that is DC current, we don't need, because it comes directly, nothing is alternating, so it comes all in one dimension. But as soon as we enter the dimension of AC circuits, voltage, current, resistance, etc., all comes and plays into multidimensionals, and the rule of AC circuits require a complex number. Okay, the amazing fact number 3 which comes up, that is, how do we represent complex numbers? We all know that we represent with this one, that is the capital C, which is called the family of all complex numbers. And this capital R, and which is a subset, it actually denotes a real number is a complex number without an imaginary part. So whenever you see in mathematics with a capital C, you understand that it's denoting complex numbers. Okay, fact number 4, amazing fact number 4. What is that? Who was the inventor of complex numbers? And we see this person, Bombelli, who is generally regarded as the inventor of complex numbers, as no one dealt earlier with complex numbers. He is the author of the treatise on algebra, which deals with imaginary numbers. This is the book La Algebra, which was published in 1578, and Bombelli gave a comprehensive account of the algebra known during that time. Now, if you want to really know more about the discovery of complex and imaginary number, I would suggest you to go to my playlist, complex analysis, in my channel Physics for Students, and you can find a detailed history on the discovery of complex and imaginary number, where much more historians and other names are there. However, Bombelli's monumental contribution to this book was complex number theory. There is another person called Girolamo Cardano, who was an Italian polymath, and in his famous book Ars Magna, he first used the systematic use of negative numbers, and he was the first to acknowledge that yes, existence of imaginary numbers are something which we take into account. Okay, coming up, amazing fact number 5. What is that? That is, what is the difference really between complex and imaginary number? This is something really good, because we deal with complex and imaginary numbers. Let us see whether there is any difference or not. So imaginary numbers are expressed in any real number multiplied to an imaginary unit. So you see 3i minus 2i, pi I, these are the real parts, and this is the imaginary part. So the imaginary number is expressed as any real number, 3, 2, pi, etc., multiplied to an imaginary unit. So here you see imaginary number iy, y is the imaginary part, and complex numbers are imaginary numbers plus numbers that has both real and imaginary parts. That means imaginary part is the number multiplied to an imaginary unit. Complex number is the complex number are the numbers plus both real and imaginary part. For example, 6 plus 8i, or 5 minus 3i plus 4 minus 7i. These are examples. So if I 6 plus 8i, you see this is the real part, this is the imaginary part, followed by your operation, that is the plus sign. So what we see is that if a plus bi is something as a complex number, and if you put a as 0, then what happens is that bi becomes imaginary, right? Because it doesn't have a real part, the real part vanishes putting up 0, right? So what we can summarize that imaginary numbers are numbers that can be written as a real number multiplied by the imaginary unit I, and complex numbers are imaginary numbers plus or minus whatever numbers that has both real and imaginary parts. So I has both imaginary and complex. Remember that the real part is A, and B and I is the imaginary part. Okay, what is the next amazing fact 6 that we have got? Now you see that yes, are there any extensions of complex number? Because we have learned that complex number are essentially extension of real numbers. So question is that, is there any extension to complex numbers? And the answer is yes. It is called quaternions, otherwise which is denoted by H. Quaternions are a number system extending complex numbers with the important distinction that they are non-commutative, right? So A and B are arbitrary quaternions, so AB is not necessarily equal to BA. Just like complex number can be visualized as being a point in a plane, the quaternions are points in a dimension which are called hyperspace. Sorry, I won't be able to show you a hyperspace here. Now, quaternions are very useful in applied mathematics, physics, computer graphics, etc. Now, again, the question is that, is there any extension of a quaternion? And the answer is yes. They are called octonions and it is denoted by O. Now, not only are octonions non-commutative, but they are also non-associative. That is, if A, B and C are octonions, then A plus B plus C is not necessarily equals to A plus within braces B plus C. So octonions can be seen as a point in an 8-dimensional hyperspace. Although not studied as quaternions, octonions do have some real application in string theory and special theory of relativity. Now again, you might ask the question that what about the extension of octonions? I'm sorry, it doesn't exist. Okay, coming to amazing fact number 7. What is that? It is that the square root of I has both real and imaginary part. Now, what do I mean by that? What I'm trying to tell is that the square root of a negative number is purely imaginary, but the square root of a purely imaginary number has both real and imaginary parts. So, square root of minus 12 will be something like this, right? So, the square root of a negative number is purely imaginary. Okay. So can we look into something like this? So we will try to prove that the square root of an imaginary number has both real and imaginary part. So let us assume a plus bi, which represent actually square root of I, and since this one equals to this one, what we can tell is that the result of should be equal to I, and we obtain to get the following: a square minus b square equal to 0 and 2ab will be equal to 1, and from there we can further deduce that a square equal to b square and a equal to 1 upon 2b. So when the first equation is solved for the variable a, we learn that the variables a and b are either equal or opposites. From the second equation, we know that the product is a positive 1/2, so the variable of a and b must be equal. So from there, what we see is that the second equation, this one, becomes 2 square equal to a, and we further solve and we get this one. So from here, what we can do, say that the number of I has 2 square roots. This is this one and this one. Square root of 2 upon 2 plus square root of 2 upon 2i, and minus square root of 2 upon 2 minus square root of 2 upon 2i. And if we rationalize or we further deduce them, we find this to be the final one. So you can see that any negative number will be purely imaginary, but the square root of a purely imaginary number has both the real part, that is the left hand side part, followed by the imaginary part. And what is the last amazing fact that we are about to encounter? That is something like this. What do you think this fraction would be? Now, what I would like to tell you is that, you see, in an imaginary fraction, it actually matters whether the numerator denominator has the I in it. That means minus 1 upon 1 would be minus 1, and minus 1 upon 1 would be also minus 1. But what is 1 upon minus I? That is minus I. And in order to prove that, I have just shown a very simple demonstration. If I take this fraction 1 upon I and I multiply that by 1 upon I get to I upon I square, which comes upon I upon minus 1, which actually shows minus 1. So these are the some 7-8 amazing facts which I think are very interesting, which are, I won't say generally taught, but these are something which are really great to know, and this generates a kind of a motivation and liking to learn more about complex number and imaginary number. I am immensely thankful for watching this video. I would request you to subscribe to my channel, click on the bell icon to get all the notification from Physics for Students. I am also available in this email ID which you can write to me. I also have a channel which is exclusive for Einstein General Theory of Relativity. Here is the link, and you can follow me further on Instagram, Facebook and LinkedIn. Please put up your comments. How do you like those amazing facts? And let me know more about this video in the comment section. And don't forget to subscribe and share my videos. Thank you, and may the God be with you.